Right. I want the video to be as fast as possible so that you don't have to spend too much time on it. So, and you can pause and think about anything that I'm going to mention for a minute at any time. So, should I zoom out one more step? Yeah, we'll zoom out one more step. Could probably slide that a little bit further. Anyway, so here, I'm going to split this up into two videos. So I have one video that I'm going to re-record where we talk about the timing diagram for this. But for now, for our first video here, we're just going to talk through what this microprocessor does. So the goal of this microprocessor is to act as a mini computer. So this has all of the critical pieces to form a simple computer out of. And so in order to act as a computer, it's going to perform a variety of arithmetic, including add, subtract, multiply, etc. We have some arithmetic operations as well as some logical operations, not, nor, and, or, etc. Lots of options up here that this thing can do. But in order to perform those operations, there are a couple of pieces that it's going to need. So the first piece that I'm going to talk about in this version of the video, I think the wisest place to start is actually up at this 3x8 decoder. So this 3x8 decoder is a little subset of this, and so depending on the code we fill in here, it will activate one particular output of this decoder. So right now the code is 111, which is 7. So it is lighting up Y7. So this is the address region. And so this acts just like pointers and such, where the address tells you what memory location to go poking around in. And so it does addressing to either read from the memory or write to it. And so you'll need to control this to tell your microprocessor which memory device to access for reading or writing. Okay, so that part's pretty straightforward. Now down here we have the memory zone, where we have a variety of memory devices. So let's talk about each type. So our memory devices, sometimes we need to read, sometimes we need to write. Now, depending on exactly what we need to do, we may have some devices that only perform one of those functions and some devices that perform both. Kind of depends what we need it for. So over here on the right are our read-only memory, which is what ROM stands for. We also have RAM. I'll talk about that in a second. But for a read-only memory, when we say that it is read-only, the microprocessor does not have access to manipulate what is in it. So read-only memory is the type of situation you might have if there is a zone of memory on some piece of your computer that your computer does not allow itself to edit. Some piece that was programmed in external before the building of your computer, quite possibly, and it remembers a number, and your computer can read that number, read that value, but it can't directly manipulate it. Now, there are two pieces to that. There's this buffer. The job of the buffer is to decide, are we reading from this location in memory at the moment? If not, it blocks the value that is stored in this ROM. Only one device is allowed to be read from at a particular moment, because every readable device sticks its output onto what is called the data bus. And so the data bus goes from memory over to computational zones, and you can use the data bus to write to things or read from them. Generally, you're reading from somewhere and sending that data over to the left side or something similar. To model our read-only memory, we're just using pins. So you, as our pretend controller of the computer, we actually have two regions of what we're going to do as the control brain of this thing. This thing does not have the ability to understand programming we could introduce a finite state machine that has that capability to act instead of us in controlling all the control lines, but we're not going to do that here. So we have this separate thing that we're also going to do where we're going to set these values to some value here, and we're just going to leave them there. And then pretend these values were locked in and our machine can't edit them, and we are not going to edit them from here either. So we're pretending that these values were permanently lodged in a read-only memory. And so that's what the pin is for. But it's a kind of weird, but we're pretending the value on this pin is fixed now. If you wanted to drop a 4-bit constant in here to make it a little bit closer to accurate, you could do that, but we're just going to pretend we can't edit this pin now, and the values are permanently in, and so it is read only. If we point to one of these devices, it may push its value onto the data bus. It will only do that if we point to it and indicate that it's time to read with one of the lines over here that we can't see at the moment, but it's right down here. We'll look at it in a little bit. Up here, between reading and writing, these are read-only devices. We also have write-only devices over here. And originally, the write-only memory was a computer science joke, because it doesn't make sense to store something in memory that you can never access again. But while it was originally a joke, it's not a completely inaccurate description of an output device. So output devices include your speakers, a printer, your monitor. Where the data is pushed out of the computer, you can write the data from the computer's perspective. We write the data to the output device, and then our computer can't see it anymore. The page comes out of the printer, the light comes out of the screen, the sound comes out of the speakers, and then it's gone. At least the data that we pushed, the version of the data that we pushed to the output is no longer accessible. Right. If the data is still in a readable device somewhere, you can go back and grab that, but you can't grab the copy that you pushed onto the write-only device. It just disappears into a non-computer accessible format. Once the speakers make the sound, that's it. So we have these write-only memory is the designation we're using it, but you can just think about it as output devices that are not further accessible once the output occurs. And then down here at the bottom are the read-write devices. And so in a computer, we call that RAM for random access memory. So there are other memory devices that are both read-write, but in this context, we're going to call it RAM as an analog for the actual RAM, random access memory, the RAM sticks in your computer. But it's just readable and writable here. So on the readable side, the buffer can kick the value from here onto the bus if it wants. And these things are writable if you activate the write line down here and point to one of these writable devices and then trigger the clock. That data will be stored into these registers. Right, and the register just remembers the 4 bits that you hand it on the A pin here. So this is the read portion, and then the writable devices have registers. The readable devices have a buffer on their outputs. And the job of the buffers is only one of them can be active at a particular moment. Whichever one that is will kick its value onto the data bus. And everything that has the data bus as an input can see it. Most of the devices that can see it will not be enabled. They will see the value but not be told to remember it, and so they will ignore that value. If we're in write mode, only one of these writable devices will be active at a particular moment. Whatever is pushing onto the bus, all the writable devices can see, but only the active pointed to and told to write writable device will actually write it into its memory. Okay, so that's the memory block, and we already talked about the addressing. So down here are the read line and the write line. If you want to read, you have to activate this. If you want to write, you have to activate this. To determine which thing you are reading from or writing to, you need to assign the pointer, the device address, which points to the cell you are interested in, the memory cell you're interested in. So you have to set that as well as write or read, depending on which you are doing. You'll also need to control these 5, we'll talk about them in a second, and clock it in order to do the writing process. You need to clock it. And when you read, it's going to come over here, and you're going to need to clock it so that one of these 2 registers picks up the value that you're reading from memory. So you read from memory and it jumps over to the computational side where you can perform operations on what came from memory. It has a few temporary storage memory blocks here in order to facilitate the computation process. So if you're writing to one of these, you need to clock it to write. If you're reading from somewhere, you're going to need to clock it to store that value either here or here to continue to compute with it. But now we're going to expand on that last piece here. So there are a couple important pieces over on this side. So let's start with the main computational driver here, the full function ALU. And so the ALU is short for Arithmetic Logic Unit. And so it can perform arithmetic operations or logic operations, and it is the unit that can do either of those things. And the way that it works is it has this function code here, so you can change the function code. So I set the function code to 7. So this ALU outputs on Y. It says here not A. So whatever value is on A will be inverted and pushed onto Y. At the moment, there is no value on A. So I'll expand on it in a second, but I'm going to read. And we're pointing to cell 7. And cell 7 contains a 0, so it's pushing a 0 onto the bus at the moment. And so this thing, the ALU is in not A because this code is 7. And so since A is 0, 0, 0, 0, not A is 1, 1, 1, 1, which on a hex display displays as F. Okay, I'm going to turn the read line off because the rest of it doesn't matter now. And we'll just set this back to zeros. Okay. So I'm going to have to demonstrate most of the rest of this. I will name a couple more pieces and then we'll go straight into demonstrating the full process. The accumulator's job is to temporarily store the value from the ALU. So when your ALU has A and B set correctly, in order to perform the operation you want it to perform, then you will activate the accumulator and clock it so that the correct computational value goes in the accumulator. If the ALU is producing junk at the present moment, and it will be doing that from time to time, we make sure not to activate the accumulator when it's producing junk so that we ignore it. We only store temporarily the result of a meaningful computation. This guy is sequential, so it can remember things or not remember things, depending on how we set it. The ALU is purely combinational, so at any given moment, it is always looking at B and A and the function and computing a Y. If we have set function B and A correctly, and we have a useful Y, we want to remember it. At various points in our computation, one or more of these may not have the correct thing on it. And during those times, the ALU is just producing whatever it happens to be told to produce at that moment. The ALU is just always presently computing, and it's the accumulator's job to pay attention to the ALU when it's producing something useful and ignore the ALU when it's not producing anything useful. And you'll see when both of those things happen in just a second. Over here, we have the D-Mux. The D-Mux's job is to take what is on the data bus and send it down the B path or the A path. And that's all it does. We have this register. If we need to manage A and B at the same time, the data bus only has room for one value. So at any given moment, the data bus can only contain one thing. So this is the ALU Input Register. And the job of this is to store the value of B. So you're going to take the value for B out of memory first, store it here, then switch to retrieving the value for A to the ALU. I'm going to pause and see what happened here. Okay, so for consistency's sake with the 1-bit pin version, I switched the D-Mux to have B on top and A on the bottom. It's not going to be a significant issue. It just changes the behavior of this pin right here slightly. So it's possible. I'm just changing it for consistency's sake. But you could absolutely create a functional version of this with A above B, and you could swap this guy around to be A with B, or you'll still be fine even if you can make this work with either this. You might stick an inverter on there to make it do exactly what you want, but it'll be fine. But I'll switch it so that B's on top and A's on bottom here. So it can take the B path, which we have this register, so we're going to store the value of B first here in the register on our first clock cycle. Then we're going to switch, access the value of A, send A down here, and then you're ready to perform the computation. So this just temporarily stores the value of B. If you need to get A and B from memory, you grab B first, store B here, then grab A, and then you have what you need and you can store it to the accumulator. So let's watch this run in one move here. So what I'm going to do is I'm going to take, let's do, which of these do I want to do? Let's do a subtraction. Okay, so I'm going to subtract A minus B. And so I'm going to write down over here the operation I intend to perform. So I'm going to store to RAM 6. I'm going to store the result, let's say, of ROM 3 minus ROM 2. Okay, so I'm going to store ROM 3 minus ROM 2. And so that's going to be my goal. So I'm going to take the value in ROM 3, get the value in ROM 2, calculate ROM 3 minus ROM 2, and then write the result into the writable device RAM 6, which is the type of operation your computer might do if you name a variable, name another variable, subtract them, and declare the result to be another variable, assign that to a third variable. So here instead, we're just referring to specific registers instead of, in the higher level languages, the name of a variable. We're naming registers instead. So we're going to take the result of the difference between these ROMs and store it to RAM 6. So I'm going to show that process one step at a time, and then I will record a second video where I note what the timing diagram looks like for this operation, but I'll separate it out as a separate video so that you only have to deal with one segment at a time. This is going to be the long segment. The other one should be pretty short. Okay, so if we would like to take the value ROM3 minus ROM2, it matters what order we pick them up in. So ROM3 minus ROM2 means that A is the value in ROM3 and B is the value in ROM2. We have to retrieve A second because there's no register. We have to pull it directly from memory and use it right then and there. For the B element, we can store it in this register for use during the second stage. So the first move we have to make is to retrieve ROM2 and get it stored in here. So we have these 5 control lines. So we'll talk through what these do after I line up these. So we're fishing a value out of ROM2. That requires us to read. So we're going to take care of that first. Oh. Okay, come on. Enable. Sorry. That's a string of multiple wrong buttons at the same time. Come on. Enable this. Okay. All right. We are reading. Specifically, we are trying to read ROM2. So I'm going to point to memory location 2. Oh, and I accidentally reset these. So this was at 7, that was at 5, that was 6, and that one was C. I think is what I had in there, yeah. Okay, and so what you can see is ROM2 is being pointed to, which slings down here and activates this enable, and it's also being told to read, so that runs up here, so both these enables are active. So the value on ROM2 is read. So when we read ROM2, that result is pushed onto the data bus. All of these other ROMs are in high impedance mode because they have at least one inactive enable. So then when they're in high impedance mode, they defer to anything else that is connected on the line. So none of the other buffer 4s going before the data bus, none of the other ones are active. So only ROM2 is actively pushing its value onto the bus. And so there's no conflict there. You can see that the bus contains a 5, which is the value we're reading from ROM2. Okay, I now need to take this value and put it into this register. So let's account for all of these. The ALU input just determines which side we project it. So I want it to go on the B side, which is low. We need the ALU register to remember this value, so I'm going to turn it on. This lever right here is to clear the accumulator and the ALU register if you want to do that. It is active low, and you want to make sure that you actually made these active low in your register, which you probably did. So if this is low, it will forcibly clear these, and you won't be able to write anything into it because it'll just keep clearing itself. So I'm going to turn it to 1, which deactivates it, and so it does not clear them and allows them to pick up a new value. Okay, at the moment, the accumulator, the ALU is producing nonsense because we don't have a value on A to calculate with. So, and the ALU is not set to subtract, which isn't a big deal because this is going to be junk no matter what, so I didn't worry about it. But I turn the input to the accumulator off so that it ignores the junk that the ALU is producing. And we also need to leave the output accumulator off because the accumulator doesn't have anything that we need, so we don't want to kick its value onto the bus, especially while the bus is being used to read. So you'll only have one of those active at a particular moment anyway. Either read or output accumulator. You'll never activate both. So that's all 5 of these pins. We're reading everything. This thing is set to remember. Everything is pathed the right way. And so when I trigger the clock, this 5 is going to make it into the register. And that's it for what we've managed to do in clock cycle 1. But this is how real computers work. You control all the lines and do it one step at a time. So we've managed to pull our value for B. into place. So we're going to switch things up. I'm going to change the direction that the D-Mux flows because we need to retrieve the value we want to put in position A, which is ROM 3. So we're still reading, but we change our address to 3 so that now we're fishing the value on ROM 3 out onto the bus instead. And so we can see that almost everything is set now. We've got A, B. All we need to do is set the ALU. Now we have to make sure it's in subtract mode, which is code 15. So we do that. So I turn off the ALU register because this is a default 0. We don't want to replace the 5 that we already have. It's not going to be a big deal if we do, but there's no reason to do it. It would have been a big deal if we had replaced it, if we replace it before finishing this computation. But as long as we remember the current value of all right, 1 second. Okay, it looks like there was a mistake on the adder subtractor. These were swapped. I had, for whatever reason, sent A to B and B to A. I just fixed it. This may have affected your file, so I'm going to post an announcement about this. Actually, I'm going to pause while I write myself a reminder. This is the fall 2021 class. I'll probably have fixed this before spring, but if I forgot. But I'm going to replace the file, so it should propagate. So if it's not this term, fall 2021, it should be okay. Okay, so I fixed that, and now it is properly taking A minus B as 2. Okay, so we set the pathing correctly. We're not replacing the 5. We don't want to wipe the 5 that we already have for sure, so we leave that unchanged. But now we trigger or we activate input to accumulator. Now the ALU is producing a meaningful value. The accumulator's job is to hold on to it. So I'm going to clock it. Okay, and there's our 2. So the job of the accumulator is now, it's got the result of our computation, which frees up this, which frees up the ALU structure over here. If you need to perform another computation on the result of our first computation, you would pass this value back through the D-Mux back in here some way, depending on what type of operation you were performing. So the accumulator just accumulates computations, right? It remembers the result of computations, and you can keep computing until it's time to write it somewhere, at which point you'll project its value over here. If you use it in a later computation, it's going to keep spinning around in here whenever you need it in order to perform a chain of computations. So it accumulates a stack of computations. You decide on what you want to compute, and it'll let you stack them up until you're done, and then we send it over to the writable device. So that was our second clock cycle. So it requires 2 clock cycles, one to fetch the first value from memory, one to get the second value and finish the computation. It requires a 3rd clock cycle to actually do the writing to location RAM 6. So we're going to change our pointer to point to location 6. We're going to stop reading and start writing. So you can see that RAM 6 is now ready to go. At least its writable side is. Its readable side is not because the read line is low. But this thing's ready to store a value. What we need to do, okay, so I turned off the read. So at the moment, nothing is pushing onto the data bus. So it doesn't actually matter which way the pathing is going because we're not, the ALU is producing junk either way, and the accumulator is not going to replace this 2. So we turn this off so the 2 stays in place. Doesn't matter what pathing we're taking. There's no reason to replace the 5 in the register. It wouldn't be a big deal if we did, but we're not going to. We're definitely not wiping the 2 that we need. And then what needs to control the bus is the accumulator. So we kick this line on. The 2 is on the bus. RAM 6 can see it. It's being told to write. It's being pointed to. And everything's good to store that to RAM 6. So we clock it. And RAM 6 now has the result of our computation. All right, so I'm going to post an announcement about the reversed pins if this is the fall 2021 class, and then update the file so that this class and later ones, if you're still working on it, in this term or in a future term, the file will be updated so that it won't have that bug. And then I'm going to record a separate video showing the timing diagram version of this. So have a good day, everybody. Bye-bye.